We now use the light clock to study length contraction, which is the shortening of a distance in the direction of motion. So we're going to take the light clock and turn it on its side and allow it to travel in the direction of motion u in a frame S. So the frame S is here, and we're observing the light clock, and it is traveling in a frame S prime that's moving with it. So let this be at t equals 0 in the S frame. There is a flash of light, and this light signal travels to the right towards a mirror, and it takes a certain amount of time to do that. So a certain time later, the light clock has got to this position, and the flash of light has traveled to the mirror. And this has happened in a time delta t1, which is the time interval for the signal to go from the flash of light to the mirror. Now recall that the length of the light clock is d, which is not necessarily the same as the length at rest. So the distance that this light clock has traveled during that time, delta t1, is u delta t1. Then the light signal is reflected from the mirror, and it travels back towards the receiver at the left, and that takes a certain amount of time. And so a certain time later, the light signal has traveled back to the receiver. And this is at a later time, so the time has already got to delta t1, and delta t2 is the time interval now for the light to go from the mirror to the receiver. We want to find the total time delta t, which is the sum of delta t1 and delta t2, which are not necessarily the same. So what we do is, first of all, let's note the distance traveled here by the light clock is u delta t2, and the distance traveled by the light signals here is c delta t1, catching up with the mirror and moving into the receiver. It travels a shorter distance, c delta t2. So first of all, c delta t1 is equal to u delta t1 plus the distance d, plus that distance d. So u delta t1 plus this distance d is equal to c delta t1. And from there, we can solve for delta t1 to start with by subtracting u delta t1 from both sides, and we get c minus u delta t1 equals d, and therefore delta t1 is equal to d divided by c minus u. During the second time interval, we have that u delta t2 plus c delta t2 is equal to d, because that distance plus that distance equals that distance, which is d. Therefore, we can solve for delta t2. We take out a common factor, and we have c plus u delta t2 equals d, and therefore we have an expression for delta t2, which is equal to d over c plus u. Now let's find an expression for delta t. So delta t is equal to delta t1 plus delta t2, and we have established that delta t1 is d over c minus u, and delta t2 is d over c plus u, and we cross multiply and take out a common factor d. So we have d into c plus u plus c minus u divided by c minus u times c plus u, which gives the difference of squares c squared minus u squared. U minus u here cancels, and then we have a 2c, so we have a 2 dc over c squared minus u squared. Then we multiply top and bottom by c, and we get 2d, so we've divided by c over here, and we've multiplied by c on the right, divided by c squared minus u squared. And that can be written further as 2dc, d upon c, and then we divide by c squared above and below, and we end up with 1 divided by 1 minus u squared over c squared. And you'll recognize this term here, or this factor, as being gamma squared, the Lorentz factor squared. And therefore, we have that delta t is equal to 2d upon c times gamma squared. So continuing, we have delta t is equal to 2 gamma squared d upon c that we've just established by looking at how light signals travel for the light clock. We know previously that there's time dilation, delta t equals gamma delta t naught. And we know from looking at the light clock at rest that delta t naught is equal to 2 d naught divided by c. Combining these results, we have on the one hand that delta t is equal to gamma delta t naught, and delta t is also equal to 2 gamma squared d upon c. Now delta t naught is equal to 2 d naught upon c. So we have 2 d naught upon c equals 2 gamma squared d upon c. So then, just equating these two terms, we can divide through by gamma, multiply through by c, and divide through by 2. And what we are left with is length contraction, because we have d is equal to d naught divided by the gamma that remains on this side of the equation. And that is the length contraction formula.